In Kadane's algorithm, you optimize using logic. But today, you optimize using geometry.
Oh, absolutely. That shift from logic to geometry is, well, it's everything.
It's a critical moment in an AI or ML interview, right? Where you have to basically stop recomputing from scratch and finally start reusing structure.
Yeah, exactly. When you sit in that interview chair, making that mental shift really dictates whether you move on to the systems round or, just get sent home.
So let's ground this right away.
Right, let's use our anchor problem for today. Finding the maximum sum subarray of size k. So imagine you're handed an array of numbers representing sequential data points, right? Like 2, 1, 5, 1, 3, 2.
Okay, got it. 2, 1, 5, 1, 3, 2.
Exactly. And you're given a window size, let's say k equals 3. Your goal is to find the contiguous subarray of exactly 3 elements that gives you the highest possible sum. For this specific array, the expected output is 9.
I want you to pause and think about how you will solve this interview coding question. Picture that array in your mind. 2, 1, 5, 1, 3, 2. Your first window of size 3 is 2, 1, and 5.
Right, the very first chunk.
Yeah, and the very next window shifts over by 1 position to become 1, 5, and 1. So visualize moving from that first subarray of 2, 1, 5 to the next subarray of 1, 5, 1. Ask yourself, which elements are reused? Which elements change? Keep that picture in your head. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
And taking that exact visualization you're holding in your mind right now, moving from 215 to 151, let's actually look at the geometry of what just happened there.
The underlying math.
Right. If you analyze that transition, you have shared elements. The numbers 1 and 5 exist in both the first window and the second window. They're basically your overlapping foundation.
They don't change at all.
Exactly. The only actual change in the data subset is that the number 2 on the far left edge was removed, and a new number 1 on the far right edge was added.
And that's the core insight, isn't it?
That is it. That redundancy geometry is what allows us to completely bypass heavy computation.
So the golden rule, the fundamental rule of this entire pattern, boils down to one mandate. Don't recompute the middle, only update the edges.
Precisely. Update the edges. Reuse the middle.
A good way to visualize this mechanism is imagine you're carrying a really heavy bucket of water to fill a pool.
Ooh, I like this analogy.
Yeah, so brute force is dumping the bucket out and refilling it from scratch at the hose for every single step you take.
Which is just exhausting.
Right. But a sliding window is just topping off the tiny bit that spills. Why would you exhaust yourself?
You wouldn't. But honestly, that brute force baseline dumping the bucket is usually a candidate's first instinct when they hear the words subarray under pressure.
For sure. Panic coding.
Right. If you were to code the brute force way, you'd use nested loops. You'd write an outer loop with a pointer, say I, tracking the start index of your window. And for every single position of I,
you fire up an inner loop.
Exactly. An inner loop with a pointer j to iterate exactly psi times, manually adding up the numbers in that specific block.
So running that on our array of 2, 1, 5, 1, 3, 2, the outer loop points to the 2. The inner loop manually adds the 2, steps to the 1, adds it, steps to the 5, and adds it. You get 8.
Right, your first sum.
Then your outer loop steps forward just one single index to the 1, and instead of reusing work, your inner loop just starts from scratch, adding the 1, then the 5, then the new 1.
You are literally forcing the CPU to perform redundant addition operations for data it already processed.
Which gives you a pretty terrible time complexity.
Yeah, it's big O of n times k, where n is the total number of elements and k is your window size. Space complexity is O of 1 since you aren't storing anything extra, but that O of n times k time complexity is just a massive red flag.
It's a fatal flaw for an interview setting.
Yeah.
I mean, it works fine on a whiteboard with an array of 6 integers, but in a production environment.
Forget about it.
Right. If you run that nested loop logic against an array with, say, 1,000,000 data points and a window size of 50,000, multiplying those operations together just drains your execution time. You'll definitely hit a time limit exceeded error on the optimal test cases.
Which is exactly why we use the sliding window mechanic to solve this, to eliminate that n times k bottleneck. The strategy here is a strict one-in, one-out protocol.
One in, one out.
Yeah. You maintain the running sum of your previous window. When you step forward, you just subtract the element that fell off the left side of the window, and you add the new element that entered on the right side.
2 simple math operations replace the whole inner loop.
Exactly.
But translating that into code, I mean, it can get a bit messy with index boundaries, right? How do we track this without getting lost and triggering an index out-of-bounds error?
Well, you manage it by visualizing the geometry of pointers. Think of a right pointer expanding the window by moving through the array, bringing new elements in.
Okay, so right brings data in.
Yes, and simultaneously you have a left pointer shrinking the window, identifying the elements left behind. Once your window reaches that required size of k, both the left and right pointers just move forward together in parallel.
Okay, I want to challenge that visualization slightly.
Sure, go for it.
Why bother visualizing two distinct pointers, a left and a right, if the window size is perfectly fixed at k? If the distance between the front and back never changes, couldn't I just use a single loop with an index I as my front edge, and then just subtract the element located at I minus k?
That is a great question. You're identifying the exact mathematical shortcut we use for fixed-size code, using I as your right pointer, and I minus k mathematically simulating the left pointer.
Right, so why visualize two?
Because interviewers are tricky. Shortly after you master fixed windows, they will throw variable window problems at you, where x is not a constant. The window has to grow or shrink dynamically based on the data.
Ah, I see.
Yeah, so if you hardwire your brain to just rely on that I minus k arithmetic trick, your mental framework shatters on variable problems.
Yeah.
Visualizing independent left and right boundaries prepares your mental model for those advanced patterns.
That makes total sense. The single loop I minus k is basically just a specialized optimization of a broader two-pointer system.
Exactly. So let's actually dry run the final industry code using that single loop structure so it's crystal clear for everyone.
Let's do it. Step 1.
Step 1, secure the edges. Always check edge cases. If the input array is empty or if k is less than or equal to 0, return 0.
Right, never jump into core logic without securing the perimeter.
Step 2, build the initial window. You can't slide a window that doesn't exist. So we sum the first k elements. In our array, 2, 1, 5, 1, 3, 2, we sum 2, 1, and 5.
Which gives us 8.
Right, we store that in window sum. And we also initialize a maxsum variable to 8 since it's the only sum we've seen so far. Step 3, the slide. We start a single for loop where our index I starts at k, which is index 3, pointing to the value 1. We take our current sum of 8, add the new element at nymsci the 1, bringing us to 9.
And then we drop the old one.
Yes. The outgoing element is at nymsci minus k. Since I is 3 and k is 3, that's index 0. The value is 2, so we subtract 2.
So 8 plus 1 minus 2 is 7?
Exactly. We check if 7 is greater than our maxsum of 8. It's not. So maxsum stays 8.
Then the loop naturally increments. I becomes 4, which is the value 3. We add 3 to our sum of 7, giving us 10.
And we subtract the element at 4 minus 3, which is index 1. The value is 1.
So 10 minus 1 is 9. That is larger than our maximum of 8, so maximum updates to 9.
Spot on. And we do one final iteration for the last element, the 2. Add 2 to 9, getting 11. Subtract the outgoing element at index 2, which is 5. 11 minus 5 is 6.
And 9 is still our highest, so loop terminates, we return 9.
That's the whole algorithm.
And if we look at the big O discipline here, the time complexity completely collapses to O of n, right?
It does, because every single element is processed exactly twice by the CPU, added once, subtracted once, no inner loops retracing steps.
And space is O of 1.
Always. We just used a couple of primitive integer variables.
So we should officially declare this pattern. This is the sliding window fixed size pattern. And if you're in an interview, you need to listen for trigger words.
Oh, definitely. The prompt gives it away.
Yeah, if they say size K or fixed length or continuous segment, those are architectural blueprints. They're telling you to deploy this exact pattern.
And this generalizes across so many domains. Finding moving averages, counting valid substrings, dealing with sensor data, update edges, reuse middle.
Speaking of averages, I want to play the role of a slightly naive candidate here.
Okay, let's hear it.
So if I need a moving average, I'll just keep my sliding window sum and divide it by k inside my loop on every single step. That way I have the average ready to go.
Yeah, no, mathematically it works, but structurally, that is a glaring inefficiency. We call that the average trap.
The average trap.
You should almost never execute division operations inside the core iteration of an algorithm if it can be avoided.
Why is that, though? I mean, to a junior dev, math is just math. Why is division so evil inside a loop?
It's all about CPU cycles. Basic integer addition or subtraction are incredibly fast for the arithmetic logic unit. They take like a single clock cycle.
Super fast.
Right. Floating point division. It's a highly complex hardware operation. Depending on your architecture, one division can consume 15 to 40 CPU clock cycles.
Oh, wow.
Yeah, so if you put that inside a loop running a million times, you are introducing a massive compounding latency bottleneck.
So the move is to maintain the sum as integers and only divide when absolutely necessary.
Exactly. Do the division outside loop or only when outputting to an external array. Avoid it in the hot path.
That system-level computational cost awareness is literally the difference between a junior coder and a systems engineer.
Absolutely.
And bringing this back to AI and ML pipelines, this pure DSA concept is actually signal processing.
It's the backbone of it. In the real world, you aren't dealing with clean arrays of 6 integers. You're dealing with continuous, massive data streams.
Right, like say you're building an anomaly detection model for a wearable health device.
Sure, an Apple Watch or a Fitbit.
Exactly. And it's streaming heart rate data at 100 hertz. So 100 integer data points every second. That raw hardware data is so noisy.
Very noisy. Electrical interference, movement, you might get a momentary spike of 220 beats per minute for a millisecond.
And if you feed that raw, spiky data directly into your neural network,
the model won't learn the true physiological trend. It'll just overfit to the hardware noise. It's useless.
So to fix that, you build a pre-processing pipeline that deploys a sliding window moving average.
Right. By passing that fixed size window over the time series stream, the algorithm rapidly computes the local average at every timestamp. It flattens out those micro spikes.
Transforms a jittery signal into a clean trend line, all before feeding it to the neural network.
Exactly.
Yeah.
And it has to execute in real time on the device without draining the battery. That's why avoiding the average trap and maintaining O of n time is mandatory.
It's so cool how a simple coding trick bridges directly to a functioning ML product.
It really is. But, knowing it isn't enough, in an interview, silence is your enemy at the whiteboard.
You have to talk them through it.
You do.
Yeah.
So here is the exact think aloud script you should verbalize while you're coding to impress the hiring manager. You say, brute force is O of n times k. We recompute overlapping elements. Sliding window reuses previous computation. We update by adding one element and removing one. This gives O of n time.
That is so clean. It proves you're actively evaluating algorithmic trade-offs, not just regurgitating syntax.
Exactly.
But pressure makes us all do dumb things.
Yeah.
What are some common interview mistakes candidates make under stress with this pattern?
Oh, there are a few classics. Accidentally recomputing the sum from scratch inside the loop. That just defeats the whole purpose.
Right, forgetting the one in, one out.
Yeah. Or miscalculating the index math, like subtracting num-psi minus 1 instead of num-psi minus k. They lose track of the geometric distance.
What about the initial window setup?
Oh, missing that is huge. They'll start sliding from index 0 and immediately throw an out-of-bounds error trying to subtract something that isn't there. And of course, the dreaded off-by-1 errors in loop boundaries.
Always double-check if your loop needs to terminate at n minus 1, or n minus k.
Yes.
And the only way to avoid those is practice.
Yes.
So we're assigning you some homework.
Grab your laptops. Your guided practice is to implement a moving average of size k. Navigate the data stream, but do not fall into the division trap.
Maintain that integer sum.
Then, for your independent homework, write the O of n code for maximum sum of size k, minimum sum of size k, and a function that counts how many windows have a sum strictly greater than a target variable x.
Love it. It forces you to adapt the conditionals without breaking the sliding structure. If we pull back for a second and look at our overarching mental model journey here, remember, in Kadane's algorithm, you optimize by decision. Do I keep this subarray or start a new one?
Right, logical evaluation.
But sliding window optimizes by structure. You're physically manipulating the geometry of the data to eliminate redundant math.
It's a huge shift in how you view data streams. But, as I hinted at earlier, mastering this fixed-size approach brings up a pretty big limitation.
I think I know where you're going with this.
I want you to pause one last time and ask yourself, what happens if the window size is not fixed?
Oh, the fluid boundary.
Yeah. What if the window needs to grow to capture a specific sum and then shrink autonomously when it hits some data constraint?
That single loop I minus k math completely falls apart.
It shatters. You suddenly need those independent left and right pointers we talked about. The geometry gets a lot more complex.
And that is exactly what we're going to tackle next time. We'll be deconstructing the variable sliding window pattern.
Oh.
So do your homework, trust the geometry, and we'll see you in the next deep dive.